In this lesson, we're going to begin to look at translations of sinusoidal functions, so translations left and right and or up and down, similar to what you have seen for other types of functions throughout your math courses. At the top of your lesson there, you have the general equations for sine and cosine functions. And it says there, when d is positive, the function is translated d units right. When d is negative, it is translated d units to the left. So here's the d value we're speaking of right here. Okay, and in addition, when there is a constant added or subtracted at the end of the equation, our function shifts up or down. So if c is positive, the function is translated up, and if it's negative, it's translated down. So we're going to have a look at a specific example here. Okay, in our first example, it says graph one cycle of the function y equals cos x minus 30 degrees plus 2. Now in this example, let's make a note that d, in this case, is 30 degrees, which means we're going to shift 30 degrees to the right. And let's also make a note here. That just reminds me, if we could go back up to your note. In some cases, D is referred to as the phase shift. Okay, so in your homework, if you come across, if you come across the term phase shift, that is referring to the horizontal translation. Okay, so D is the phase shift. Okay, so in this first example, we could say the phase shift is 30 degrees. Oftentimes, if the phase shift is reported as a negative number, that means it's shifting to the left. Okay, so in this case, we're shifting to the right, so the phase shift would be positive 30 degrees. And our C value is 2, which tells us we're going to be shifting 2 units up. Now what I would like to do here quickly, though, is just sketch in the graph of y equals cos theta itself so that we can see where the key points on this graph move to. So I'm going to use a scale of 30 degrees, but I'm only going to mark off the 90-degree intervals. So 90, 180, 270, and 360 in both directions. Okay, and we'll fill in the scale on our y-axis. Okay, there we go. And let's sketch a y equals cos theta quickly. So it starts at 1. We have our first root at 90, then negative 1, then 0, then 1. We can connect our points. There we go. Other side looks the same. Okay. Now then, one way we can graph a translated function is just to take the key points all along our graph and translate them. So if we're moving our graph 30 degrees to the right and 2 units up, that means if I take the point at 0, 1 and move it 30 degrees to the right and 2 up, then that point will now be at 30 degrees and 3. If I move the point at 90 degrees and 0, 30 degrees to the right, so 1 square to the right and 2 units up, it will now be here. So basically every key point, then I'm moving 1 square to the right because that will be 30 degrees and 2 units up. Okay, and the last one would be off the graph, but it would be roughly here. Okay, moving backwards now to negative 90 and 0, 1 square to the right and 2 up, 1 square to the right and 2 up, 1 square to the right and 2 up. Then I can connect my dots, and there we have our translated function, y equals cos x minus 30 degrees plus 2. And I should label my original here as y equals cos x. All right, let's look at another example. Okay, the next example is y equals sine x plus 45 degrees minus 3. Now, be careful when there is a plus sign in brackets, okay, because the general form of the equation is always x minus d. So in other words, this really would have been written as sine x minus negative 45 degrees minus 3. Okay, so this is where your d value is actually negative 45 degrees, or your phase shift is actually negative 45 degrees. So we will be shifting 45 degrees left. C is negative 3, which tells us we will be shifting 3 units down. So we're going to do the same thing, which is to create a quick sketch of y equals sine x itself, and then we'll translate each key point 45 degrees left and 3 units down. Let's use the same scale we had in our previous example. Okay, so again using a scale, using increments of 30 degrees, but only marking off every 90 degrees. Okay, y equals sine theta starts at the origin. Sine 90 is 1, sine 180 is 0, and it oscillates back and forth, which you know now from your last lesson. Okay, same thing on the other side. And one thing for sure by now, you need to be able to create the graphs, okay, for y equals sine theta and y equals cos theta fairly quickly, as we just did. All right, we're going to take all of the key points here and move them 45 degrees to the left, which will be like a square and a half. Okay, if 3 squares is 90 degrees, then 45 degrees would be half of that, so a square and a half. So a square and a half to the left and 3 units down. So starting at the origin, we're going to move this point a square and a half left and 3 squares down. Okay, so here's our new point right there. Square and a half to the left and 3 squares down. Square and a half to the left, 3 squares down. And you get the idea. Okay, there's part of our graph. Square and a half to the left, 3 squares down. And take all your key points and do the same thing. And we will end up with our translated curve, which we will label y equals sine x plus 45 degrees minus 3. Okay, in your next example, we're asked to determine the equation given the translations in words. So the first one says the sine function has been translated 56 degrees to the right, so there's our phase shift, and 3 units down. So 56 degrees to the right tells us that d equals 56 degrees, and 3 units down tells us that c equals negative 3. So in our equation, in brackets, we would have x minus 56 degrees, and after the brackets we would have minus 3. So y equals sine x minus 56 degrees minus 3. In our next example, we have a cosine function, which is being translated 120 degrees to the left, which means our d value is negative 120 degrees, and 2 units up, which tells us that c is equal to 2. Fill that into our formula. So y equals cos x minus negative 120 plus 2, or in simplified form, y equals cos x plus 120 plus 2. Hopefully that is legible. Okay, and that concludes this lesson.